Hi, I want to talk. This is the last part of the Wednesday/Friday lecture, and I want to talk about three theorems, uh, uh, 3 or 4 theorems, uh, about completeness, compactness, and Cauchy sequences. And these all have a similar flavor that these are statements in Rn. Some of them are general statements. And the proofs will involve using a lot of facts from R. So let's start by stating the theorems, so you have a clear reference for them, and then we will discuss the proofs. So first statement is we define what is a complete metric space, that is where Cauchy sequences converge. And the first statement says that Rn with the usual metrics that we have so far discussed, namely dp, d infinity, and you could focus on p equals 2 if you want. All of these are complete spaces. So here we don't see anything new. Cauchy sequences still converge. Okay. Second theorem. If you have any complete space, if you have a closed subset of that space, then that closed subset is complete. And third theorem, this requires stating a definition about bounded subsets. So we define a subset of a metric space X to be bounded if there exists some center and some radius that the ball K is contained in that ball. So as a picture, we have some center and some ball in our set. K should all be contained inside that. Now, if you have a subset of Rn, there's no loss of generality if you assume that your x0 is equal to 0. And then the condition is just that there exists a radius such that K is in B 0. In terms of this notion, we can say that a subset of Rn, K, is compact if and only if two conditions hold: K is closed and K is bounded. This is a very important theorem in optimization, as it guarantees when you can find subsequences that converge. And some of these are familiar. So boundedness corresponds to the assumption that we had in 131a, namely that the sequences are bounded. In fact, this will play a role in the proof. Closedness is needed because when we construct the subsequence that converges, it will at first converge in Rn, and we will need that it will converge actually to a point in K, and that for that we need closeness. And an example of this application is that if you take the closed unit disk, so all the points at distance at most 1, including 1 from the origin, well, this set is bounded because it's contained in the open unit ball of radius 2. I've used 2 here because I need a little room, because these are open balls and this is closed. And the set is also closed. This can be verified. There's actually a video on this this particular point, but you can also prove directly that this is closed. So by Heine-Borel, this set is compact. And relating to this, there are two general statements, and I will at least state these, prove one of them. If X is compact, then X is also complete. So any compact space is also complete. And then some of the aspects of the general theorem hold always. If you have a K subset of X is compact, then K is closed and K is bounded. So some of the facts hold generally. Okay, so let's start by discussing the proofs of these. And let's do it in a way where we emphasize the logic and the ideas and the structure. So first of all, we are proving that something is complete. That means that every Cauchy sequence converges. So let's fix a sequence that is appropriate. So fix xn in R, and let's actually replace this n with a d so we don't have to misuse the letter n in two different ways. So xn is a sequence in Rd. Fix xn a Cauchy sequence. And we want to conclude that xn converges. And our idea for this will be that we know that Cauchy sequences converge in R. So if we could say something about the components, we would be in a good place. So our setup is just we fix a Cauchy sequence. Okay, so we want to reduce to what we know, Math 131a and Rn. So let's look at the components. So we have that for every component, I, 1 through d, we have that x and I minus xmi is less than x and I minus xmi to the power p. Well, this is actually just equal. Now, if we make this inside bigger by adding the differences from the other components, then this is less than sum j equals 1 through d of x and I minus xmi to the power p, 1 over p. Sorry for the notation being there. And this is the same thing as the distance between them. Distance p, xn. So we get that the components are closer than the distance between them. So this is fairly intuitive in general. So we want to apply the one-dimensional result. So let's first add this to the setup because we seem to need this. So for every epsilon positive, there exists an n1 such that distance xn to xm is less than or equal to epsilon if n is bigger than m, is bigger than n1. Okay, this holds for every epsilon. So fix an epsilon and positive and choose n equals n1. Then for all I, and for all n bigger than m bigger than n, we have xni minus xmi is less than dxn xm, which is less than epsilon. We'll need a little bit more space here, so I'll move this statement down. Okay, so we have that this distance, provided you're that far, is less than epsilon. This holds for every epsilon. So for every I, x and I minus the sequence of real numbers, let's call this an now, to emphasize this is a sequence of real numbers, is Cauchy. Now, a Cauchy sequence converges. So since an is Cauchy, it converges. So there exists an xi in real numbers so that component-wise, these vectors converge. Now define x equals x1 through xd to be a point in Rd. Again, I'll need to move this statement a little bit down. So this is our point. Okay, this we define. And well, we now have component-wise convergence, and we have identified what the limit is. So let's summarize this proof now. But we get that xn converges to x component-wise. That is limit as n goes to infinity of x and I is equal to xi for all I. And therefore, by the theorem we did last time, we're done. By theorem from Monday lecture, so week 2-1 lecture, limit n goes to infinity of xn is equal to x. So component-wise convergence in this case gives the full convergence. Now there's general logic here that comes up in a lot of completeness proofs that's good to notice. First, we reduce to some simpler case, so in this case component-wise convergence. We use that component-wise convergence, and this often involves some estimate, to find a component-wise limit. So we first do for every I, we look at the limit of the components. And this is how we define what the limit is. So this is a way we get a handle on what the limit ought to be. And then in the summary, what we get is we get component-wise convergence, and we can convert it to actually convert convergence to the full thing. And this is why we proved that component-wise convergence means convergence in the full space. Now, an example of this is that suppose vi are vectors in Rd, so that the norm vi, 2 norm, that is sum over the components bij squared, square root, and so that sum of vi squared, the norm I equals 1 through infinity, is less than infinity. Then define xn as the sum of partial sums, and this is the sum of vectors. Then this sequence is Cauchy, and it converges so we can define the infinite sum vi. So we can use this idea to prove that sums of vectors converge, and this plays an important idea in many places. This is the analog of absolute convergence of vectors. And okay, proof? Well, I won't do the full thing, but the crucial estimate is that if we look at the distance between xn, so d2 distance between xn and xm, so for n, and we have to choose an n so that this works. This is the same thing as the norm, xn minus xm, 2. By expressing it as a sum, you get that this is the same thing as summing from m plus 1 up to n, the norms of vi. 2, but this thing can be made small for big enough m because this converges. For n m bigger than n, because that converges, absolutely convergent. So the logic is actually the same as in R, but with a norm. And this is a powerful idea that's useful in many places. Okay, So we proved that Cauchy sequences converge in Rn, that is, R is complete. Now I want to say that if you have proven that some space is complete, for example, Rd, then any closed subset of it is complete. Indeed, examples are an interval in R is complete, that we already discovered, but also the closed cube with its metric being the usual metric in R3 is also complete. So you can use this theorem directly to prove that. You don't have to prove it, but okay. Let's again use the setup. So let's fix Xn now in E, a Cauchy sequence. We have to use the assumptions somehow. Well, Xn is also in X and Cauchy in X because the matrix is the same. So there exists an X, it converges in X, such that limit n goes to infinity of Xn is equal to X. Now conclusion is that since E is closed and limit n goes to infinity Xn equal to X, then X is actually also an element of E. That is, Xn converges to X in E. And this is the crucial thing for completeness, is that we have a limit point in E. And you saw this in some of the examples in the introductory part where completeness or convergence of Cauchy sequence fails, mostly for the reason that the limit fails to be inside the set E. Finally, about compactness. This is the hardest notion, so it definitely takes some time to learn, but one of the most important theorems is this Heine-Borel theorem, is that if you have a closed and bounded subset of Rn, then it is compact. And let's do again this change of notation, because we will work with sequences and I like to index sequences with D. Okay, so this is an if and only if statement. We have to go both ways. Let's first go from closed and bounded to compact. And what we have to prove for compactness means that every sequence has a convergent subsequence. So let's fix Xn as sequence in K, any sequence. And by boundedness, we'll use this assumption. There exists an R positive so that K is a subset of B0 R. Well, then, if we look at the components, and this we just discussed, then for every I, the absolute value of the ith component is less than the distance of Xn to 0. And it doesn't matter what metric you use here. So any metric that you use. So I'll leave the notation, any of the usual DP metrics. Then that's less than the distance to 0, which is less than R, well, because Xn is in K, which is a subset of B0R. Okay, why did I do this? Well, for every I, the sequence X and I, so I is now fixed, and this is a sequence in N. To emphasize this, let's call it AN, even though for every I we have a different sequence, is bounded. Okay, so we found a bounded sequence that now works. Okay, so let's first fix I equals 1. So we have x and I is our sequence, which is bounded. And by theorems for 131a, and again, we want to reduce, there exists a subsequence nk, and I'll put a subscript here 1 because we will need to modify it still, so that x and k1, which is a and k1, converges, because we are doing it for a bounded sequence of real numbers. Okay, so this gives us one subsequence where the first component, so let's draw these, we have xn1, xn2, xnd, and we get the first to converge. But the problem is that we have all these others that we don't know anything about. But there's a trick. Sometimes this is called the diagonal trick. Is that once you've made the first component converge, we can make also the second one converge. So next, define x and 2, we look at the second components, but only along the subsequence. And define this as AK. This time we look at those values. Now, AK is bounded, so there exists a subsequence of nk1, so some selection of indices here. So this gives us nk2, so that x1 and n2k and x2 and 2k converge. And the reason for this is that if this is a subsequence of the previous one, this still converges. So a subsequence of a convergence sequence converges. Okay, so we get the second component also to converge. Well, we do this for each of the components. So now, recursively, choose n, j, k, a subsequence of nj minus 1k. So choose for each j equals 3 up to d. So the next one where we haven't defined the subsequence, so that x, and if we follow that subsequence, we look at the first component up to the jth component, that these all converge. And this is always possible because these are bounded. Okay. I know this is rather complex, so it takes a while to absorb this idea. And I'll draw a picture of this. But we get all of these to converge. So then we look at xd. Now consider the subsequence ndk. Then all components x, I, n, k, d converge. So X and KD converge because it converges component-wise. So there exists an X such that limit K to infinity of X and KD is equal to X. And since K is closed, and this X equals in RD, X is in K, so X and D converges in K. This is what we wanted to show. We found a subsequence that converges. Now, there is a useful way of picturing this. So let's draw, we have our sequence x1, x2, x3, x4, x5, dot, dot. And the components of these are x11, x12, x1. I'll just draw the three-dimensional one because it's the same idea in general. So you get this table of values, x31, x32, x33, dot, dot, dot. In the general case, we have xn1, xn2, xn3. And we know that if we look at these columns, so in this case, we have three columns, the red one, blue one, and a green one. These are all bounded. And these are bounded sequences of regular real numbers. So what that means is that we can first choose a subsequence to make the first one converge. So we first consider this one, and this fixes some subsequence like this is n1, n2 is 3, and then dot, dot, dot. And maybe we've chosen 5 here. I didn't write the components here. So along this subsequence, this object converges. But we want also this to converge. So second, we make the second component converge. And that happens by choosing a further subsequence. So we choose some of these elements. We choose n21 to be, say, this, but maybe we skip this one in the second step. That is, we choose n22. So we choose a further subsequence of them. And this time, we still have convergence of 1 because we only choose among the rows where we get convergence of the first component. But then we also get the second one converged. Now, if in 3 dimensions, we would be left with a third component where we would have to go through this argument again. But that's the main idea. Okay. So now, if we want to go the other way, so from compactness to being closed and bounded, the natural way is, in this case, to do is by assuming, and this is often the case with compactness, is by contradiction, is to say that this does not hold. So suppose not closed and open. And closed and open here is in parentheses. So this is not true. Well, then it is either not closed or not open. Okay. Well, then there are 2 cases because there's an or statement here. Case A, it's not closed. Well, what does it mean to be not closed? It means that there exists a sequence xn in Rd, so that, and this is a sequence of points in K, so that limit of xn is equal to x is in Rd, but x is not in K. So this is the assumption, but the conclusion fails. So this means, and this is what I mean by stating the negation. So we have a sequence of points that converges, but it does not, the limit point is not in K. Now, since Xn is, since K is compact, there exists a subsequence Xnk so that limit K goes to infinity, Xnk is equal to some Y in Rd. But subsequential limits, and this Y limit is not just in Rd, it's in K. Subsequential limits are equal to limits if they exist. And this is an exercise. This will be also on the homework next week. So subsequential limit is equal the full limit. So this means that X is equal to Y because the first one is equal to Y, the second one is equal to X. And this belongs into K. So X belongs into K, and we have there X not in K. So this is a contradiction. So this is what we derived the contradiction in this case. Okay. Let's say not bounded. So then there exists. So for every R positive, we have that K is not a subset of BXR. K not subset of B0R. If it's not a subset of B0R, what does it mean? That for every R, there exists a point outside of it. Now let's apply this now to many R's. This is a common idea. So then, for every n natural numbers, there exists an xn that's in K and xn not in B0 n. We look at radius n balls, n is becoming larger and larger. We're choosing points that lie outside of them. So pictorially, we're choosing x1 here, x2 there, and they all lie in K. Well, so they're going further and further away, so they should not converge, and this is what we wanted to say. Well, since K is compact, and there exists a convergent subsequence, so there exists an nk so that limit K goes to infinity, xnk is equal to some x in K. But another useful simple exercise is that limit K goes to infinity, distance xnk to 0 is equal to the distance of x to 0. But this distance is less than infinity because x is some element of K. And this here is equal to infinity because distance of x and k to 0 is bigger than nk. And limit K goes to infinity if nk is equal to infinity. And this is our contradiction in this case. So this concludes the proof that the direction that a compact set must be closed and bounded, because if either of these fails, you can derive a contradiction. So there are some general facts corresponding to these that I won't now prove, is that if you have X is compact, then X is complete. And the crucial idea of the proof is that you take a Cauchy sequence we don't know it converges yet, but there exists a convergent subsequence so that this the subsequence converges. And this is similar to proofs in 131a that if you can prove that if xn is Cauchy and has a convergent subsequence, then it is actually the full sequence convergence. And the reason is that the subsequence gets very close to the limit point, but xn is very close to its subsequence as well. And by a close examination of the last proof that we gave in full detail, we can also conclude that if you have a compact subset of a metric space, then it's always closed and bounded. And the argument is very similar that you do before. So you can actually, the closed part is, if it fails to be closed, you can derive a contradiction exactly the same way. If it fails to be bounded, it's a little bit more tricky because of the way we defined it, but it works exactly the same. You can find a sequence of points somehow going very far away in the space. So thank you for your attention.